Hello and welcome to Deeksha Karnataka YouTube channel, and in the PU1 series of Masterstroke, today I am going to discuss properties of solid and properties of liquid. If you study these chapters, you can expect one question each. Now the chapter, sometimes the questions from these two chapters are very easy, which you can simply answer if you go through the lecture. Sometimes you may need to do a little bit of calculations, and understanding of the concept is also important. So I request you, if you want to answer these two questions, go through this lecture completely. And as usual, let me show you the chapter highlights. In the properties of solid, we are going to discuss modulus of elasticity, three moduluses, Poisson's ratio, elastic potential energy, we are going to discuss. Also in properties of liquids, we are going to discuss streamline, flow, Bernoulli's principle, viscosity, speed of efflux, which is very important concept for KCET, and surface tension. So these are the concepts that we are going to discuss from these two chapters, and without any delay, let us start. So basically, when we are talking about properties of solids, basically we are talking about how a solid will behave if you apply external force into it. Okay, so far we have considered all the objects are rigid bodies. Okay, so if you apply force, the object starts moving. Now imagine that the object is not rigid. Rigid means all the molecules are fixed at its place. Okay, no matter how much force you apply, it will only give rise to the motion of the object, but it will not produce any deformation. Okay, deformation means when you got slapped by someone, your face becomes red, right? Just joking. So basically it means that when you apply force on some object, what happens? The shape of the object changes. Okay, it can happen with anything. For example, when we fall down, our body breaks, our bone breaks, so it is a deformation. Okay, so deformation means anything, any small changes that happens with the application of forces. Okay, for example, wear and tear, that we say. Okay, if you are wearing a shoe for a long time, slowly the shoe gets worn off. Why this happens? Because you continuously applying force on the shoe, and it cannot handle the deformation for a long time, and slowly it starts to come off, right? Similarly, every object in nature, if you apply force on it, it tends to deform. Okay, and in this chapter basically we are discussing about those kind of deformation. Now what is how to deform an object? Now our objective is to deform something. How to deform an object? So for that you have to apply external force, obviously. Okay, and in this chapter, instead of talking more about force, we will talk about stress. Yes, stress. So stress is something that we all are facing. For example, you are having a stress that, okay, my KCET exam is near, my COMET exam is near, I have to prepare for that exam, and during that time you are feeling stress. Basically the exam is giving you some kind of force, applying some kind of force on you, forcing you to study, and you are feeling stressed. Okay, so that is stress. Now because of the stress, what happens is that the object deforms, and that deformation is we called strain. Okay, so that incident left a strain in my life, right? So that means some thing happened to you, and because of that something remains sometimes it can be permanent, sometimes it can be temporary. So the thing is that the strain means when you apply stress, the object deforms, and that deformation is called strain. Okay, let's understand more detail in scientific way. Okay, when a body is subjected to a deforming force, a restoring force of equal magnitude but in opposite direction to the applied force is developed in the body, the restoring force per unit area is known as stress. So basically when you have an object, suppose just let me change the color. Suppose you have an object, and if you apply some external force to the object, okay, the object, what it will do, it will try to stop this deformation, and it will apply a reactionary force in the opposite direction, exactly equal. Okay, exactly equal to the force that you have applied, and force suppose the surface area of this is given by, where the force is applied, say the surface area is A, then force divided by area is called stress. Okay, this is denoted by a symbol sigma. Okay, this is denoted by a symbol sigma. Now, so restoring force, remember that when you apply external force, the body produces a restoring force, okay, equal and opposite direction, and that is called stress. Okay, and what is strain? The change in its dimension is called strain. When an external force acts on it, there are three ways an object which of a solid may change its dimension. Okay, so for example, now what will happen if you apply stress? For example, you have a rubber band. If you apply some stress into it, it expands. Okay, similarly, if you have a steel wire also, if you apply enough force on it, it also expands, right? So when you apply force, the object's shape changes. Okay, the shape, size, length, there are many kind of changes. Okay, so here we are talking about three main changes which through which object can change its shape. Longitudinal strain. Longitudinal strain means simple one-way traffic. You apply some force, the object expanded in the same direction. Okay, so that is called longitudinal strain. Next is tangential or shearing strain. Shearing strain means you apply some force on the object. Okay, it changes its direction, but it is not in along the length of the object. Okay, for example, you twist a wire, or you have a book. If you apply force on the top of the book, the bottom of the book remains stationary, the top of the book slides slightly. Okay, that kind of force is called tangential. When the force is tangential, the strain is also tangential. Okay, hydraulic strain. Hydraulic strain is, for example, you imagine that you have a liquid in a container. You apply pressure into it. The shape of the liquid compresses. Okay, that is called hydraulic strain. Now, stress is the cause, strain is the effect. Remember, stress is the cause, strain is the effect, right? Also remember that strain is basically a dimensionless quantity. Stress, what is the dimension of stress, by the way? Dimension of stress is same as pressure. Force by area. Force is mLt to the power of -2 divided by area is L square. So dimension of stress is mL to the power of -1 T square. Okay, remember this. And strain is a dimensionless quantity because it's a ratio of its change in some quantity divided by the original quantity. For example, longitudinal strain is change in length divided by change in divided by original length. So both are the ratio of the same quantity. That's why longitudinal strain is basically has no dimension. Tangential strain is measured by angle theta. Okay, theta is a dimensionless quantity. Hydraulic strain, again, change in volume divided by original volume. This is also a dimensionless quantity. Now, out of the out of the three, these two is applicable only for solid. The third one is applicable for solid, liquid and gas as well. Okay, second one, tangential, can be applicable to liquid in some extent, but longitudinal is only solid. Tangential is, say, solid plus liquid, and hydraulic is solid plus liquid plus gas. Everyone undergoes hydraulic strain. Clear? Any doubt? Don't forget to join in the live session. Next, Hooke's law. So now what happens is that when we apply some stress, okay, the strain develops. Now there is a relationship between stress and strain. Okay, Hooke, obviously someone who experimented with this, so he did an experimentation and he plotted a graph, and then he came up with a law called Hooke's law for small deformation. Small deformation means change in the length is small. If he mainly did it with length only, longitudinal strain only. Small changes in deformation, stress and strain are proportional to each other. Okay, so stress is proportional to strain. Strain, not this sign. even though this is also epsilon, but it is written like this. Okay, so even this is also epsilon, okay, but that epsilon we generally write for free space permittivity. This epsilon is for stress. There are two types of epsilon, okay, one is flat one is curved one, okay, just to differentiate between two different quantities. Okay, this chapter there are a lot of symbols, anyway you don't need to remember all of those, understand the basic concepts, that is sufficient, and few formulas. Okay, don't go into the too much into the symbols. Now he says that within elastic limit, in another word it can be called that within elastic limit stress is proportional to strain. Okay, now if you see that the graph has few parts, okay, up to this point A the object remains elastic and it obeys Hooke's law. Okay, it obeys Hooke's law. Obeys Hooke's law means if you apply some external stress, the object will expand, change its shape and size, and if you remove that stress, the object will come back to its original position. Okay, now if you continue further increasing the stress up to this point B, okay, the stress is no longer proportional to strain. That's why there is a curve. Curve means it is no longer proportional, but if you remove the object, it will still come back to its original position. Okay, the object deformation does not happen yet. Okay, so even though the proportionality is no longer valid, but the object will come back to its original position. From here also you can come back. So basically it is like, for example, your exam is approaching, you are studying, you are preparing well. Okay, so you are studying, you are going in the proportionality limit. Those who are studying are in the proportionality limit. Those who are not studying, they are slowly their stress is increasing, strain is also increasing. Stress is increasing, strain is increasing. Okay, so up to this point, if you still have time, that if you still start studying, you can still reduce the stress and you can still go back to the original position. But beyond this B, okay, if you do not study at all, what happens? You will have a permanent backlog. You will not be able to complete entire syllabus. This is a permanent set. Okay, this is called permanent set. That means once the B point is crossed, okay, the proportionality obviously is no longer valid, and when you after that point, if you release it, it will come back only up to this point C. Okay, even if for a small stress, the strain will be very high. Even for a small force that you apply, that is small stress you apply, the strain will be very high. Okay, and even if you release that, remove that stress, the object will come back here and it will have a permanent deformation. There will be a permanent deformation. Okay, now you can still go up to point D. Okay, point D, even if you release it at point D, it will still come back to point C. Okay, up to point B it will come back to 0. Okay, up to point B it will come back to 0. It is called yield point. Okay, yield point. This is called yield point. Yield point means it will still come back to the original position. But if you cross point B, okay, immediately for a small stress the strain increases rapidly, and if you release it, it will only come back to point C only. Okay, and this is permanent deformation. The object will be permanently deformed. Now up to this point D, it is still proportionality limit. That means it will still come back to C. Up to point D, it will still come back to C, but after this point D, if you keep on increasing, it will reach a point which is called fracture point. The object will break. Okay, so it will no longer able to handle the stress. It will break. Okay, it will break, and it will this D point I think is called brittle point, and beyond that it is fracture point. That means the object will break apart. So if you apply too much stress on a string, after this point E, the string will break. Right, so this is the fracture point. Now for objects such as rubber band, etc., they are not super elastic. Even though we call them elastic, actually they are not elastic. Elasticity means you apply stress, you release it, they will come back to its original shape. Okay, elastic, for example, if you apply enough stress, it will always show you a permanent deformation. Steel wire, on the other hand, have a very high elasticity. Even if you apply enough stress, it will again come back to its original position. That's why our buildings, bridges, roofs, etc., they are all built by steel wires. Okay, steel has a very high stress content. Okay, it can withstand a lot amount of stress. Now, Young's modulus, there are three modulus of elasticity. We will need to learn about them one by one. So first one is Young's modulus. Tensile strain is directly proportional to the longitudinal stress. Tensile stress or longitudinal stress. Okay, longitudinal stress means force applied along the length. Okay, tensile strain is directly, tensile is nothing but along the length. Okay, if you apply a force along the length, so you have a wire. Okay, if you apply a force here, so force per unit area is the stress, and it will change it in its shape. Suppose original length was this much, it will extend it by some small amount, say delta L. The original length is say L. Then the ratio of these two quantities is constant. Why constant? From Hooke's law. Okay, obviously within elastic limit. Okay, this is valid only within elastic limit. If you go beyond elastic limit, this is not valid. Young's modulus is not valid. Okay, so tensile strain is directly proportional to longitudinal stress, and the constant of proportionality is called Young's modulus. So F by A divided by delta L by L is called Young's modulus. Okay. Next is ratio of hydraulic stress to the volume strain is called bulk modulus. I think there is one small mistake. It will be first one will be stress, second one will be strain. Okay. Anyway, ratio we are talking about, but stress by strain is constant. Remember, stress by strain is constant. Okay, so bulk modulus is denoted by symbol K. Bulk modulus is denoted by symbol K, and it is volume stress. Volume stress means you are compressing the entire volume. So force is applied from all sides, and we basically trying to reduce its volume or trying to increase its volume. Okay, then stress by strain is called hydraulic stress or volume stress. Okay, or bulk modulus. Next is shear modulus. Shear modulus means, as I explained, suppose you have a book. Suppose you have a book normally like this. Okay, now if you apply a force on this book along the top portion, keeping the bottom portion fixed, what will happen? The book will deform like this, right? The book will deform like this. So this angle will be theta, okay, in radians. So if the force that you have applied, the area that through which you are applying, this is the stress, and divided by this strain, this is the strain, this is the measurement of the shear strain. Okay, shear strain. So ratio of shear stress to shear strain is called shear modulus, and it is denoted by G. Okay, so this is very simple basics of stress and strain. Now let's move on. Now also remember that there was a question that we have a spring. We have a spring. Okay, if you stretch the string, what are all the stress acting on it? Okay, so what are all the stress, not strain, what are all the stress acting on it? Shear or longitudinal or hydraulic or anything, any combination. So remember, when you have a spring like this, if you stretch it, obviously you are stretching it along the length, so longitudinal stress will always be there, and along with that tensile stress will always be there. Okay, longitudinal and tensile can be interchanged. And because it's a spiral, okay, because it's a spiral, there will be some twist happen. Okay, there will be some twist happen in the spring. So that twist is basically shear stress. Okay, that is basically shear stress. Twisting means if you take something and you twist it, okay, and the shape changes, that is also because of the stress. And spring obviously curved, so shear stress will always be there. So it is basically shear plus tensile. Okay, remember this. Now let's move on to a question. A thick metal wire of density rho and length L is hung from a rigid support. The increase in the length of the wire due to its own weight is. Y is Young's modulus of the material of the wire. So thick metal wire of density rho and length L. So here we have thick metal wire. Okay, and what is the weight of this wire? Weight of this wire is mg. Now what is m? Mass is given by rho into volume. Mass is given by rho into volume. Now when the object expands, now what is volume? Volume is area. By the way, so let me write that as well. Volume is area into length. Volume is area into length. For any object, three-dimensional object, if you know the area, if you know the length, you can find its volume. Area into length is the volume. So mass is given by rho a L, right? And weight is given by, what is weight? Weight is mg, which is given by rho a L into g. Don't worry, most of them will cancel and we will get an answer. Okay, now they ask you increase in its length because of its own weight. So increase in its length because of its own weight. Now Young's modulus is defined by Young's modulus is defined by force divided by area divided by change in length divided by original length, right? We are trying to find what? We are trying to find this quantity. We are trying to find this delta L. Okay, delta L we are trying to find. This quantity is we are interested in. Okay, now let's move on. So from here we can write y into delta L by L equals to F by A. Okay, is equal to F by A. We are interested in what? Delta L. So delta L will be F into L divided by A into Y. Simple. Whenever, as soon as you understand the problem, write down the variables and slowly simplify them. Now what is force over here? The force is nothing but the weight. Okay, so the weight itself is the force. So from here we can write delta L equals to rho a L G, rho a L G into L, this is the force, into L divided by area into Young's modulus. Okay, now what? Now area cancels and we get rho L square G upon Y. So this is the change in its length because of its own weight. I think this came in 2024, I think. Okay, so rho G L square upon Y. Okay, now let's move on to the next part. Poisson's ratio. What is Poisson? Poisson does not mean the thing that you drink and die. Poisson is the name of a person. Okay, Poisson. It is not poison. Okay, Poisson. Poisson. If you pronounce it properly, even I cannot pronounce it properly. It is Poisson. Okay, the ratio of lateral strain and longitudinal strain is called Poisson's ratio. Okay, now this is lateral. So this is lateral, say epsilon I, and this is longitudinal. Okay, so this is longitudinal. Longitudinal is long, and lateral is represented by sigma I. Okay, again I messed up. Sorry, just a second. It is not this symbol. It is slightly different. It is this one. Okay, Okay, so it is longitudinal, lateral by longitudinal. That means when you apply a force, for example, I gave you an example of string one, or when you apply force on, say, a wire, okay, and if you apply some force on it, what will happen? Its length increases. So length increases means what? You are not adding any extra material. So if length increases, then the diameter of this wire will definitely decrease. Okay, so the wire becomes narrower. So in original, suppose the diameter was d, now the diameter is d minus delta d. Okay, original length was L, now the length is L plus delta L. Now, based on the material, obviously that value can change. Okay, so if you stretch the object, its diameter decreases, its length increases. Okay, and that's why the Poisson ratio comes into picture. For example, the Poisson ratio for steel is very good. It is considered 0.3. 0.3 is very good for Poisson ratio. That means the increase in length does not change its volume too much. Okay, now Poisson ratio can be negative for certain material. Okay, actually practically it is 0 to 0.5, and for theoretical value it is minus 1 to 0.5. The range of Poisson ratio, this symbol nu, okay, Poisson ratio is greater than minus 1 and it is less than equals to 0.5. Okay, this is the Poisson ratio, theoretical limit of Poisson ratio. Practically greater than 0, but for certain material you can design a material in laboratory where you will get a Poisson ratio which is negative. Okay, the maximum value of Poisson ratio is 0.5. Remember that the limit, the maximum value of Poisson ratio is 0.5 when the volume is unchanged. That means if you expand that rod, okay, its length increases, breadth decreases, but overall volume remains unchanged. If that happens, then the Poisson ratio is 0.5. But we know that a material has a lot of gap in between them, okay, molecular bonds and etc. So they are not exactly tightly packed. So volume not always remain constant. Okay, volume changes. And because of that, Poisson ratio for an ideal material will be 0.5. 0.5 is not possible practically. Some material have a very high Poisson ratio, 0.4, 0.5, 0.4, 4.2, 0.42, but not very close to 0.5. 0.5 is for ideal material. If you stretch the material, its volume, if it is unchanged, then only Poisson ratio will be 0.5. Now remember this value. Why I am discussing this so much? Because it came in one of the previous year that a material is stretched so that its volume remains unchanged. What is the value of Poisson ratio? Okay, you can calculate that, you can do that mathematically, but you can simply remember that the volume is unchanged. That means Poisson ratio will be 0.5. Okay, how to do that? You can use this formula to do that. Okay, differential formula is nothing but sigma is equal to d. Okay, let me write diameter like capital D. D of capital D divided by capital D divided by D of L by L. Okay, so using that you can find the Poisson ratio, and Poisson ratio there is a negative sign. Negative sign is why there is a negative sign? Because if you increase the length, the diameter decreases. If you compress the length, the diameter increases. So one quantity is increasing, another quantity is decreasing. That to signify that there is a negative sign always. Okay, so this is the way you can find that at what point the volume will be, if volume is constant, how the Poisson ratio is 0.1. By the way, we will solve it in PUIQ section. Next, elastic potential energy density. So when you stretch a string, okay, or stretch a wire, or change its volume, or change its shape by applying shearing stress, okay, it always tries to come back to its original position. okay, and because of that it basically stores a kind of potential energy. So if you do some work on some object, and if the object wants to give you back that work, then it is called potential energy, right? If you lift a book from ground to the table, okay, and if you drop it again, it will again fall back. That means it wants to give you back that energy, that the work that you have done, right? So the energy stored in that is called potential energy. Okay, so potential energy density is what? Potential energy density is nothing but potential energy stored per unit volume. Okay, potential energy stored per unit volume is called energy density. And here it is very simple to give you that it is actually stress into strain. Potential energy density is stress into strain. In terms of Young's modulus, it is Young's half Young modulus into stress square. Okay, strain square. Epsilon is strain, so Y into strain square is the potential energy density, or in terms of symbol you can write half sigma epsilon. This is also true. Both formulas can be used from problem to problem. Okay, now let's move on to the next chapter, properties of fluids. Okay, now here we will start with pressure. Okay, so what is pressure? Pressure is when you apply a force on a fluid, on a liquid, okay, the force per unit area is called pressure. Now remember that the dimension of pressure is again the same as stress, that is F by A. Dimension of pressure, dimension of pressure, dimension of stress, and dimension of Young's modulus. Okay, in fact any modulus, bulk modulus or shear modulus, they all have the same dimension, ml to the power of minus 1 t to the power of minus 2, ml to the power of minus 1 t to the power of minus 2. Okay, this is the common dimension for all these three quantities. Now Pascal's law. Whenever an external pressure is applied on any part of the fluid contained in a vessel, it transmitted undiminished in equally in all directions. So if you have in a container, okay, suppose you have a ball filled with water, or a balloon. Okay, balloon is not good example because balloon can stretch. You consider a solid ball. Okay, inside the ball you have a fluid. Okay, you have some liquid inside it. Now if you try to compress it, okay, if you try to compress the ball by applying some force from all sides, the force or the pressure will be transmitted in all parts of the fluid. It will not stay there, it will transmit all parts of the fluid. And if you make some holes in the ball and if you squeeze it, the water will come out with equal speed from all sides. Okay, water will come out with a common speed from all sides. That is the Pascal's law. Okay, Pascal's law says that if you have a closed container, if you apply force apply pressure into the fluid, okay, in fluid we always mention pressure. So whenever pressure wherever you apply the pressure is equally distributed in all parts. That is Pascal's law. Application in hydraulics, there are a lot of application based on Pascal's law. Now few things that we have to remember is called gauge pressure. The terms can be confusing, that's why these terms we are using. Gauge pressure. Gauge pressure means what? Suppose you have a container containing water. Okay, let me draw it here. You have a container containing some water or liquid, any liquid. What is the pressure at this point? The height of the water, say, is h, the density is rho, okay, the gravitational constant is g. Then what is the pressure at this point? Now here pressure will have two components. One component is due to the liquid column, one component is due to the liquid itself. Okay, no air is there. Okay, no air. If you put it in vacuum also, this will experience this pressure. This pressure is called gauge pressure. Gauge pressure is the pressure due to the liquid itself. That is called gauge pressure. We have done this derivation in our childhood. Pressure equals to rho gh, right? Rho is the density, g is gravitational acceleration, h is the height, right? And now in this class in PU1 actually you have learned it. Before that this derivation was there in Archimedes principle, I think class 9th. Okay, gauge pressure is P equals to rho g h. What is total pressure? Total pressure is when you add the external atmospheric pressure to this pressure, okay, then the total pressure is P plus Pg plus Pa. Gauge pressure plus atmospheric pressure is the total pressure. So total pressure means atmospheric pressure included. Without atmospheric pressure included, it is called gauge pressure. So if you see somewhere you mention gauge pressure means the old pressure that we have learned, P is equal to rho g h. If you see total pressure means you have to add atmospheric pressure. Okay, that's it. Now let's move on to flow of fluid. Now fluid, what is the meaning of fluid? Fluid means which likes to flow. If you leave it as it is, it will flow. Okay, if there is no container, it will flow. For example, air, water, they all flow, right? And that's why the name fluid. Liquid and gases are called fluids because they like to flow. Now based on how they are flowing, okay, we can say two things: whether they are moving in a turbulent motion or they are moving in a streamline motion. Now streamline motion is what we are interested in. All the laws, all the theories that we will study in this chapter, they are for streamline motion only. Turbulent motion is chaotic motion, there is no law to govern them. Now you may have seen when you open a tap water, you see this fuzzy water, this is a turbulent water. But if you see clean small water drop coming out of the tap, then it is a streamline water. Okay, generally if the water is, if you open the water at high pressure, generally the water is turbulent, but if you open the tap slowly, okay, and if it is falling very slowly, you generally get a streamline motion. Streamline motion means what? Streamline motion means all the liquids, all the liquid particles in a container or in its path, they are all traveling in the same direction. If all particles travel in the same direction, then that kind of motion is called streamline motion. But this is streamline. But suppose one of them is not traveling. Suppose some of them is traveling in this direction, some of them are traveling in a rotation, there is a whirlwind. Okay, so in between some are traveling in the direction, so this is called turbulent motion. Turbulent motion is easy to draw. Any random motion is turbulent motion. When they are streamlined, we generally say in English also, sometimes we say we have to streamline it. Streamline means we have to make everything move in the same direction. Okay, the flow of the fluid is said to be steady if at any given point the velocity of each passing fluid particle remains constant in time. The path taken by fluid particle under a steady flow is a streamline. It is defined as the curve whose tangent at any point is the direction of fluid at that point. Okay, so if you take the tangent, it will always give you the direction of motion. It can be curved path. For example, if you have a curved pipe, the liquid can travel in a curved path, but if you take the tangent will provide the direction of the fluid motion, then it is called streamline. Streamline means all the particles are moving in the same direction. Let's move on. Bernoulli's principle. Before going into Bernoulli's principle, we have to understand equation of continuity. Equation of continuity we have learned in current electricity, and in this chapter, both chapters same thing. In current electricity it was current and area. In this chapter it is velocity of the fluid and area. Okay, so current electricity, if you remember in drift velocity into area is constant, right? So in that case it was drift velocity of electrons into area. In this case it's velocity of the liquid into area. So remember that suppose we have a horizontal pipe, horizontal flat pipe, okay, having two different cross-sectional area, and fluid is flowing through this continuously in streamline motion. Then this area is A, the velocity of the liquid at this point is V, and if this area is A2 and velocity of the liquid coming out is V2, then A1 V1 is equal to AT V2. Okay, so whatever total mass, and it comes from the conservation of mass. Okay, the principle of continuity or equation of continuity is based on conservation of mass. This is a very common MCQ in your PU1. Okay, not in KCET but or KCET, but in PU1 final exam, this is a very common MCQ question. Okay, so basically this is based on conservation of mass. So whatever mass is entering, the same amount of mass has to come out. Okay, in incompressible fluid, that means liquid is not getting compressed inside the pipe. So whatever mass is coming in, the same mass has to go out. But remember, this is a horizontal flat pipe. Now the pipe is not flat. Pipe is, suppose it is lifting a water. The cross section is different and the heights are also different. So liquid is basically pushed, say it is being pushed from ground floor to top floor. Then what? Then though that continuity, equation of continuity is not alone, it is not valid. So here you have to apply Bernoulli's principle. Okay, Bernoulli's principle says that P plus half rho V square plus rho GH is constant. Okay, from this we get two things. First of all, pressure. This is kinetic energy of the fluid and this is the potential energy of the fluid. So this is basically conservation of energy. This principle is basically based on conservation of energy. Okay, this is potential energy density, mass divided by mass. So this is potential energy density, this is kinetic energy density, and this is pressure. So this quantity, if you add them, they will be they will be constant. Secondly, what? Secondly, these all three quantities have same dimension. Okay, so in some cases might be they will ask you dimension, but just for information, just so that you know that all three quantities have same dimensions. That's why you are able to add them. If they had different dimensions, you will not be able to add them. Okay, clear? And there are few applications of Bernoulli's principle. Nothing is important, just formula. Remember the formula and the context of the formula. That's it. Now let's move on to one important concept which came across various years in KCET and KCET both exams. This concept is common, which is called speed of efflux, Torricelli's law. So basically, what is speed of efflux? Suppose you have a container, you have a closed tank. Suppose we all have water tank in our houses, right? So that water tank, if you make a hole in that, don't do it. If you make a hole in it, the liquid will start come out. So the speed of the liquid with which the liquid is coming out, okay, that is called speed of efflux. Okay, speed of efflux. The liquid which is coming out of that hole, okay, with what speed the liquid is coming out, that is called speed of efflux. Now it depends on the conditions. First of all, if the entire tank is closed, suppose you have closed the lid of the tank, it is completely sealed. So in that case, the pressure inside is constant, and if you make a hole, the speed of efflux will be different. But if you open the top portion of the tank, and if you apply, if you make a hole, the speed of the liquid coming out is different. Okay, the formula, you have to remember this formula, little tricky, little difficult. Okay, but you have to remember the basic formula. You have to remember, which is for open container. Okay, open container, speed of efflux is square root of GH. Easy to remember. Okay, with gravitation also we have seen this equation. So V1 equals to square root of GH is the liquid which is coming out of a tank. Okay, and speed of efflux for a liquid coming out when it is in closed tank, okay, it is rho GH is there plus 2 into P naught minus PA by rho. Okay, P naught is the pressure inside the fluid, P naught is the pressure due to the liquid, gauge pressure, and PA is the atmospheric pressure. Okay, P naught minus PA by rho. Rho is the density of fluid. Okay, in case of open container, very simple, square root of 2GH, but in case of closed container, there will be a component for pressure difference as well. Okay, so obviously speed of efflux is more when the container is closed, right? Now let's move on. This formula based question came, I think, once in KCET and once in Comet K as well. Dynamic lift Magnus effect. Okay, dynamic lift means what? Now when an object is moving through a fluid, okay, now a solid object is moving through a fluid, okay, what happens is that if it is moving in a straight path without any spin in it, okay, the object will move in a straight path. Okay, if there is no spin, what will happen? The object will move in a straight path. Okay, the object will move in a straight path if you apply no spin in it. Now if you apply now Ravichandran Ashwin, whoever you are fan of, okay, Ravichandran Ashwin, when I was a kid he was a good bowler. Harbhajan Singh, okay, now those players have retired anyway, some of them plays in IPL. So the bowler bowls with the spin in it, okay, when the bowler bowls with the spin in it, the ball start to lift. Okay, so there is people call it flighting. Okay, those who watch cricket, they know that flight a ball. Why this flight happens? Because the bowler applied a spin in it, and because of the spin, the object tends to go up. Okay, the object tends to go up. So now if you see that it is not only going in the forward direction, it is not only going in the forward direction, okay, it is going in the forward direction, but it is also going in the upward direction. So the resultant motion is like this. So upward motion is there, forward motion is there. Forward motion is obviously because the bowler is bowling it in the forward direction, but it is applying some spin on the ball. So because of the spin, the ball starts to go up. Okay, and this is called Magnus effect. This is called Magnus effect. Okay, those who watch chess, they know Magnus Carlsen, nothing to do with him by the way, but this effect is called Magnus effect. Magnus effect is the lifting of an object due to spin. Lifting of an object due to spin in it is called Magnus effect. Now let's move on to the next concept, viscosity. Viscosity is like shearing stress, but in case of fluid. Okay, shearing stress is what? You apply some force on the object bend or change, deforms, right, in the application of the force, and that is called shearing stress. Now here same thing happens, but it happens in case of fluid. Why it happens? So let us understand that. So when there is a fluid, okay, the fluid is basically, suppose a river. Very easy example is a river. So this is the river bed. Okay, river bed. This is the river bed. River bed means the bottommost portion of the river. So now river is trying to flow in this direction. River is trying to flow in this direction. What will happen? The layer which is exactly attached to the bottom of the river bed, it will not move. They will try to stick there forever. Okay, it will not move. Okay, because liquid is not a very solid object. Obviously it makes layers. Okay, it makes layers. You can consider a liquid is basically forming of different layers. Okay, and each layer moves with a different velocity. Okay, because of the constant kind of friction between them. Okay, it is sometimes called friction for fluids. Okay, fluid friction is viscosity. Okay, so basically the layer which is exactly directly in contact with the river bed, it will not move. With the layer which is slightly above that, it will move, but it will move very slowly. Whereas the layer which is at the top, it will move with the fastest possible speed. Okay, so the speed of fluid is more on the top than in the bottom. Okay, so because of that, when a fluid moves, it moves in different separate layers, and because of the friction between these layers, there is a drag appears. This is called drag. Okay, sometimes called drag force. And This drag force occurs because of the property of a fluid called viscosity. Viscosity is sometimes also called fluid friction. Okay, now expression for viscosity is given by, viscosity is force upon area divided by velocity by length. Okay, this is the velocity gradient. This is sometimes called velocity gradient. Okay, velocity gradient. So velocity at the top most layer is v, bottom layer is 0, and the length is say del L. Okay, then v by L is called velocity gradient. V by L is called velocity gradient. Why? Because bottom layer is 0, top layer is v. So basically it's how the velocity is changing across its length, that is called velocity gradient. Okay, and F by A again almost similar to that of the stress, right? Pressure of the fluid here. F by A, pressure divided by velocity gradient, is called viscosity, but this is not, V by L is not a dimensionless quantity, by the way. Velocity gradient is not a dimensionless quantity, it has a unit. So unlike Young's modulus and bulk modulus, the viscosity is slightly different, right? Now, one very important law is Stokes law. So this is the viscosity. Viscosity is there everywhere, but you can only feel it when you are trying to move through it. Okay, it not only happens for the fluid, but if an object is dropped in that fluid also, as the object is moving, the object is also experiencing that viscous force. Okay, so if you take suppose you have a pond or a water body, you take a stone, you drop it, the stone when falls through the liquid, it experiences that drag force. The drag force tries to stop the stone, but stone is heavier, it will continue to fall, and it will fall into the under the lake, right? So when a body falls through a fluid, it drags the layer of the fluid in the container with it. The drag force is given by F is equal to 6 pi eta RV. Okay, so this is the drag force. This is the expression for drag force. Now at some point what happens, suppose a stone is falling through the fluid and there is a fixed weight of the when the object is falling in the fluid, there is a force acting downward, generally weight of the object. Okay, and there is a drag force which is acting in the upward direction. This is the drag force. Now at some point what happens is that and drag force is directly proportional to velocity. As the object is falling down, its velocity is increasing, and as the velocity is increasing, the drag force also increasing. Drag force is not constant, it is not a constant force, it is increasing force. Okay, at some point of time what happens is that this drag force and the weight of the object becomes same. Now as soon as that happens, what happens is that the body stops accelerating. So the body is in equilibrium now. In terms of force, there is no external forces acting on the object, right? So net force is 0. Net force is 0 means what Newton's first law says, that the object will move with a constant velocity. Okay, so the object attains a constant velocity because the net force acting on that object is 0. Okay, and because of that what happens is that the object moves with a constant velocity. That velocity is called terminal velocity. That velocity is called terminal velocity. The expression for terminal velocity is this. If you want to remember, you can memorize it. I have not seen a question based on this formula, but terminal velocity as a term can be important, so you have to remember and understand what is terminal velocity. Terminal velocity is basically the constant velocity when an object falls through a fluid. Okay, if you drop a stone in the liquid, the object attains a constant speed, that is called terminal velocity. For example, a paratrooper drops from a plane, okay, and it opens the parachute, because after some time the paratrooper gains a constant velocity, and the main idea of the parachute is to increase the drag force so that the object can quickly attain the terminal velocity, and terminal velocity is as low as possible. Okay, so that is the main purpose of the parachute. Otherwise the person will continue falling and it will attain terminal velocity. don't worry, but the terminal velocity will be so high that when it falls on the ground, he will be completely flattened. Okay, but if he has a parachute, because of the high drag force, the terminal velocity is less. Terminal velocity is less, so that when it falls on the ground, it can survive the fall. That is the main thing. Okay, now few more important thing, that is surface tension. Surface tension is basically when there is a fluid or liquid, okay, mainly liquid. When there is a liquid, what happens is that the liquid tend to stay in place. Okay, if you have a water, okay, even though the liquid top of the water can be bouncy, it does not do that any such thing. Okay, because the liquid always try to stay flat, and that property of fluid is called surface tension. That happens because of the surface tension. Okay, now explanation of surface tension in detail, theory of surface tension is very long. I am not going into that detail. One beautiful picture over here, a water bug sitting on top of a water pond, and as if there is nothing there. Why it is possible? Because of the surface tension, and there are some small hair present in its legs, so that the surface tension can be increased, and because of the higher surface tension, it can stay on top of the water body and it can find its prey. Okay, surface tension, the expression for surface tension is force divided by 2L length. Okay, based on the different conditions, you have to calculate the surface tension. You may need to calculate the surface tension. Another thing is capillary rise. Again, no question came in the few previous year paper, but anyway, there is no harm in remembering this formula. So capillary rise is given by 2s cos theta divided by rho gr. So what is capillary rise? Capillary rise is if you take a straw and if you put the straw into a liquid, okay, the liquid level inside the straw increases. Slowly the liquid level goes up, and that height is called capillary rise. Okay, so capillary rise is nothing but the rise of liquid. We may have seen, we have done it when we are kids, right? We used to take straws and put it into the water and see water level increases, right? So basically this is called capillary rise, and if you decrease the pressure here, the capillary rise can be increased, and that's how we drink cold drink and juices out of the glass, right? Very old mango shake, we put the straw and sip it, right? And that is because if you decrease the pressure on top, slowly the capillary rise height increases and you keep on drinking the fluid. Okay, now capillary rise depends on the contact angle. So contact angle is the angle with which it makes. Okay, meniscus of this fluid makes with this. Now remember one very important thing, there is a very common question, not in KCET but in JEE and NEET, this kind of questions were asked. Suppose this is the capillary rise, the height is h. Now if you cut the tube here, if you cut the tube over here, will the fluid will continuously fall from here? Will it fall? Okay, so there is a law which governs it, and that law says that no, the capillary rise cannot make this infinite fountain. Okay, the height will, the liquid will stop exactly at this point. Okay, basically the liquid will not be able to make this angle, contact angle. In this case, contact angle will be just flat. Okay, and because of that, the liquid will not be able to rise any further. It will stop exactly at that point. This angle is possible only at the top position, otherwise this angle is not possible. So the capillary height will be adjusted at this maximum position only. So if the height of the capillary is less than that of the capillary rise, then liquid will no longer go up, and it will not create an infinite fountain. Okay, so infinite fountain means the idea is if you cut it, liquid will try to go up and you put some filter on it and it will create a fountain. That is not possible. Okay, remember that if you cut the capillary at a height less than the height of the tube, it will not create an infinite fountain.